Well, so are you able to see it?
Yes, sir.
Okay, so maybe I'll try to. This is my first experience I'm doing on this, this way. So, okay. So thank you, Pooja, for your kind words about me. Now, the topic of the talk, as you've already said, is Schur Hopf formula and Lie exterior square. And in this talk, we shall describe the Schur theory for multiplicative Lie algebras and demonstrate as to how it unifies the Schur theory for groups, Schur theory for Lie algebra and Schur theory for Lie rings. It also prompts to introduce a new K2, which encompasses the Miller K2 and additive K2, which is really the cyclic homology. As we all know, Schur in 1904, while looking at the problem of lifting a complex projective representation of a finite group. So, you know what is a finite group? Let me, if I can come on the, this my, well, I don't know what to do, how to do it. Yes. Stop sharing. I wish to yes. What is I wish to come to this whiteboard. I have to share whiteboard. Whiteboard. Where is that whiteboard? I'm sorry, I'm not able to. But anyway, I'll.
It's okay, sir. You can directly open whiteboard, sir. That will be visible to us.
Yeah. Directly, I have to type it, is it?
Yes, sir.
Anyway, I'm not able to do it here in my. Anyway, so I'll just try to read it. So, see, Schur in 1984, while looking at the problem of lifting a complex projective representation of a finite group G, a projective representation of a group is simply a homomorphism from a group G to PGNC, the projective general linear group, which is GNC over center of GNC, to a linear representation. So you have a homomorphism from a group G to the quotient group GNC over GNC, and you have to lift it to a homomorphism from G to GNC, whether we can do it or not. So he came across this problem, and in this he came across an abelian group as abstraction to this possible lifting. Whether we can lift it or not, this depends on a group which he introduced, and this group is called really in today's language it is the second cohomology group H2G, the second cohomology group of G with coefficient in the trivial module C star. The group of non-zero complex numbers, and this is termed as Schur multiplier of the group. So this is something which he introduced, and this is indeed the group of all central extensions of C star, equivalence classes of group extensions, central extensions of C star by G. For a finite group G, he also established the formula. The second cohomology is isomorphic to, this is R intersection FF. FF is the commutator subgroup of F over RF. RF is the commutator subgroup of generated by the elements of the type X, where A belongs to R and X belongs to F. Where this 1 to R to F to G to 1 is a free presentation of G. So this is a free presentation of G. F is a free group, and F to G, this is a surjective homomorphism whose kernel is R. So this formula is termed as the Schur Hopf formula. A crucial step in proving this formula is the fact, which is again due to Schur, that if the commutator subgroup of G is finite, whenever is always finite whenever the central quotient G over ZG is finite. And you know, there is a famous theorem of universal coefficient theorem in the homology theory of groups, or in topology also. H2, the second homology group, is the group of homomorphisms from the second homology group, H2, with coefficient in Z to C star. And of course, this homomorphism is not non-natural homomorphism. Consequently, for finite group G, H2G star, the second homology group, is isomorphic to R intersection FF over RF, which is your the second homology. So for arbitrary groups, of course, they need not be isomorphic. Note that all the three define functors from the category of groups to the category of abelian groups. Thus, there are three aspirants for the term Schur multiplier. Indeed, Schur multiplier, I mean, there is always a controversy. What should be termed as a Schur multiplier of a group? So there are three aspirants here, as you see, the second homology group and the Schur formula, which is isomorphic to the second homology group when G is finite, and the second homology group also, which is isomorphic to this group when G is finite. A similar theory for Lie algebra, Lie rings exist, and we introduce Schur theory for multiplicative Lie algebra and Lie algebras, and demonstrate that it unifies the Schur theory together with the Milner K2 and cyclic homology. So let me first say a few preliminaries about multiplicative Lie algebra, the introduction of multiplicative Lie algebra. Indeed, multiplicative Lie algebra was introduced by Eels in 1993, and I guess what was the reason behind the introduction of the the concept of multiplicative Lie algebra, and I perhaps feel that this is how it must have been introduced. This must have been the motivation for the introduction of this. So indeed, he attempted and succeeded partially to describe the analog of Magnus-Witt theorem. The Magnus-Witt theorem, which is really, which says that if you take a free group and look at its lower central series and central series quotients, the central series quotients form Lie algebra. And if you take the direct sum of those Lie algebras, then it is a free Lie algebra. It is a free Lie algebra on the abelianizer F of AB. So roughly, this is what going to have the information about commutators, the commutators which are everywhere present in every group. So the identities which are present everywhere in the group. So for any group now, so let me first introduce, for any group G, the commutator operation here is denoted here, satisfies the following identities, as you all know. The commutator of XX is 1, the commutator of XYZ is commutator of XY, and the conjugate of XZ with Y, which is equal to XY, and the conjugate of X and the conjugate of Y. And here also this the third identity for every XYZ, where XY denotes the commutator XY, X inverse, Y inverse as usual, and YX denotes the conjugate this of X. These relations are termed as trivial commutator relations. Now, following Lode, indeed, Lode introduced this concept with some topological problems. The group G, cap G, which G generated by the symbol, this symbol. So treat them as symbols subject to the relations this X cap X equal to 1, and these relations which you see is similar to the first, second, and third for G. And he called this the non-abelian exterior square. You all are familiar with the exterior square of the vector spaces, which is simply the universal exterior operations on the vector spaces. So it is a generalization of that you may say. So if the G is abelian group, it is just the same thing. So consequently, we have a unique homomorphism. So it satisfies all these first, second, third identities. So therefore, from the universal property, it has a unique homomorphism eta from this exterior square to G, subject to this condition eta xy is equal to this. Indeed, it is universal in the sense that if you have if F is any homomorphism from G to another group G which preserves commutator in the sense this, then there is a unique homomorphism F bar from G cap G to G to G cap G to G. I'm sorry, here G K at the place of K here is G, such that this condition is satisfied. So you see that a map from a group G to another group K. Sorry, K is K. It's okay, right? So if you have any map from G to a group K, which simply preserves the commutator, so it is some kind of weak homomorphism, then it is converted into a homomorphism from the exterior square G to K. So you can, just as you know, in case of, for example, in covering space theory, you have the lifting problem. So similar thing is happening over here. So we have this homomorphism. The kernel of eta can be viewed as a group of non-trivial commutator relations on G. So given any group G, it already satisfies all these three conditions, first, second, third, but it may satisfy some more conditions, and what more identities, what more specific identities are satisfied for this particular group G is that information is incorporated in this kernel of this map F bar. This group is denoted by HG, which is indeed and it can be further viewed as the second homology, integral homology of G with coefficient in J. Of G also, I'm sorry, here is K, with the coefficient in the trivial G module J. Thus, for instance, the commutator identities in G are derivable from the above three identities. If all the commutator identities, all the relations among the commutators will be satisfied, will be derivable from the three identities if and only if this kernel HG is trivial. So HG is the kernel which I have described over here. In case G is finite, we shall see Schur Hopf formula that this group is isomorphic to G star. Indeed, we shall see is not the proper term. I should say that it is already known. For group, it is already known, and that was the Schur Hopf formula, which was proved by Schur in 1994. So there are still some useful invariants, namely H0G of G, which is you look into these symbols X cap Y, which are mapped to the identity of the group G, such that the commutator of X and Y identity, that means X and Y commute. So therefore, you see that the group generated by this is a subgroup of that group HG, which is really a generalized, so to say, Schur multiplier. And the group B0G, which is your HG, which is the quotient of HG and H0G. So we are taking the relations modulo these relations that X and Y commute. So that is B0G is still another invariant, important invariant in mathematics, which is your called the Bogomolov multiplier, and it is intrinsically related to a problem which was posed by Noether. Namely, given any faithful linear action, so linear action means representation of G on V, whether the quotient V by G is a rational variety, or equivalently, if you look into the function field of V and look at the field of G invariants, then whether this is this is an extension of C, obviously, but whether it is a purely transcendental extension of over C or not. So the abstraction to this is this Bogomolov multiplier, which we have described over here. Right, so this is an important invariant which has a lot of applications in the geometry. Note that for each U, belonging to G, the map X cap U mapped to U cap X. I mean the conjugation of X with U cap the conjugation of Y with U in these symbols respect the defining relations which define the defining relations for this exterior square. Thus, for each U defines a homomorphism, automorphism indeed, from G cap G to G, which is given by this. In turn, therefore, G acts on this. Further, there are, so here comes the real point. Further, there are two more identities satisfied by the commutator identities, as you see here, which are here. The Jacobi's-like identity, XY commutator, the commutator of Z and Y, the inner conjugation, and this, this is a Jacobi-like identity. If the inner conjugation is trivial, for example, in an abelian group, it is just the Jacobi identity because the commutator becomes the identity. So it is just the Jacobi identity. In Lie algebra, it is the Jacobi identity which is satisfied. And here also, the fifth identity, fifth one, is your Z of the commutator of the inner conjugation of the commutator is the conjugation of their inner conjugations. This is fifth identity. So these are the two more identities which are satisfied by the commutator identities, which are satisfied in every group. Now, if one wants to develop the similar kind of theory, then you note here that we cannot describe the group of commutator relations of G modulo the above all five commutator relations the way we describe the commutator, the group of commutator relations modulo the three earlier commutator relations. The reason is because here is the ternary operations which are involved. So therefore, that symbols X cap Y or similar kind of thing probably is not cannot be. It's not possible. So this perhaps was the reason for conceiving the concept of multiplicative Lie algebra as I understand. So this is something, but however, the Ellis actually attempted to check whether these five universal identities which I have described here, the commutator identities, are sufficient to describe all commutator identities. In other words, something like the result of Magnus, whether we can terminate somewhere these things. So this amounts to check. So this really amounts to check if the eta described earlier, X cap Y goes to the commutator XY, is a G invariant, G equivalent. We have already seen that G acts on the HG, the G cap G. It acts on G cap G, and so on the kernel also. So G equivalent homomorphism and HG, the kernel of eta is generated by these elements which are the fourth this identity union. It has to satisfy this commutator identity. I mean this identity also. So union this as a G subgroup of the exterior square. Obstruction to this conclusion is the invariant of G, which is of our interest, which is really of our interest, and this perhaps might have motivated the Ills to concretely introduce the concept of multiplicative Lie algebra. So therefore, I introduced it differently here: a G equivalent homomorphism eta cap here from G cap G over HG cap. So this HG cap is the G subgroup of G cap G generated by generalized Schur multiplier to G, and this homomorphism defines and is defined indeed by the multiplicative Lie algebra structure G dot star in the sense of the following definition, which was introduced by which was given by the Ellis. So now I properly define, I formally define the multiplicative Lie algebra as was introduced by the Ellis. A multiplicative Lie algebra G is a triple G dot star, where G is a set, dot is a group, or dot G together with dot is a group, star is a, these are two binary operations, G dot is a group, not necessarily abelian, and for all X, Y, Z in G, the following identities as we have already witnessed, the 5 identities similar to that are satisfied. So this is what is our Lie algebra. So if you take G, for example, an abelian group, then this will turn out to be a Lie ring, integral Lie rings, integral Lie rings. And if you go to the Lie algebra, then obviously it will turn out to be Lie algebra. So the multiplicative Lie product will usually be denoted by a star, and all these operations star will multiplicative Lie algebra. The identities in the following proposition can be easily verified. It is it's an easy verification, simply depending on the defining identity of the multiplicative Lie algebra. It can be very easily defined. So evidently, the subgroup generated by X star Y is a normal subgroup of G and is denoted by G star G. As observed earlier, any G equivalent homomorphism from G, I'm sorry, here it is the wedge. It is not the intersection. It is G with G defined oblique this, the quotient group this. I'm sorry, this is wedge, not this. To G is a multiplicative Lie algebra. However, we have few. So if you want to have example, you just look at the homomorphism from G to G. So one can perhaps generate plenty of examples of G cap G to H cap G. See, if Sumit is in the audience, he may perhaps look into this and try to generate several examples, which perhaps is important for several other considerations. So to G gives a multiplicative Lie algebra structure. However, we have a few concrete examples of multiplicative Lie algebra. The trivial multiplicative Lie algebra is there. You just take a star to be the trivial one, X star Y to be 1. The commutator operation is every G group G with commutator operation is already a Lie algebra. Every Lie ring at a Lie algebra is a multiplicative Lie algebra is already observed. And here is a different kind of Lie algebra. If you take a group G and look at the group Ig of all inner automorphisms of G and consider the standard semi-direct product, Ig is acting on G as automorphism, and in the product, the semi-product given by the multiplication is given here. So GIH, this is the inner automorphism determined by H, IL is the inner automorphism determined by K, so L, and the product is defined by GIH of K and IHK, where IH denotes the inner automorphism determined by H. It can be easily checked that this is a multiplicative Lie algebra with respect to the Lie product this, where Ig denotes the inner automorphism group. So this is a Lie algebra. Indeed, one can observe what kind of map from G cap G to H cap G to G defines this map, this Lie algebra structure. Evidently, this is a non-trivial proper multiplicative Lie algebra with respect to the Lie product defined over here. And if you take G to be a nilpotent group of class 2 and phi endomorphism of G to G, then we have a multiplicative Lie algebra structure on this given by this. This is a consequence of the observation which I had motivated to define the multiplicative Lie algebra. So you have these operations here, and this proposition is again a similar thing. You take any G equivalent homomorphism from G cap G to G, satisfying this property will define multiplicative Lie algebra structure. This is a particular case of what we observed earlier. So G with a, and if you are given G to be a group with a trivial Schur multiplier, that was HG, then the Lie algebra structure is uniquely determined by G equivalent homomorphism GZ to G as described previously by the previous question. This is almost a trivial observation. Now, as usual, homomorphism and sub-algebra and Lie ideal, the ideal, etc. can be defined as here. So, for example, G is a multiplicative Lie algebra, the group center, the group center. So, multiplicative Lie algebra is a group also, and together with a star, operation star satisfying certain properties. So, we can talk of the center of the group, all the group things we can use. So center of the group G, and it turns out that the center and the Lie center, here is the Lie center, which is X belonging to G, said that X star Y are ideals. Ideals means they are Lie subalgebras, they are closed under the subalgebra product, and this condition X star Y belongs to that set for all. So these are all ideals. It can be easily verified. Now, to establish the analog of the Schur Hopf formula, and to say that the Schur multiplier of the multiplicative algebra, if we view it the way the group, in case of group it was viewed, one is forced to have the concept of free multiplicative algebra, the concept of the notion of free multiplicative algebra, whether it exists or not in the category of multiplicative algebra. That is a question. And whether we can talk of the concept of presentations of multiplicative algebra. We can talk of presentations of groups, as you already know. So whether we can talk of free multiplicative algebra and presentations of the multiplicative algebra. So this is something which is essential and which is, which is essential for all the things which we think of. So this is what we have to what we introduce here, and the concept of free multiplicative algebra, the concept of universal free object in the category of multiplicative algebra exists, and how it exists, the construction. You see, usually the universal objects, the existence of universal objects are described with the help of the constructions you really construct. And you see there is forgettable functor from the category of multiplicative algebra to the category of groups. You just forget the structure star, so there is a forgettable functor, and one is always in search of the adjoint to this functor, and it is the object free objects are really the adjoint. This define the adjoint to those functors. So this is what we describe here. So how to describe the free multiplicative algebra? It is a little subtle, and I just demonstrated it here. So you just look into the bracket arrangements with on X. So what are the bracket arrangements? So the bracket arrangements are just the union of the bracket arrangements of the different weights. So for example, this beta nx is the set of all bracket arrangements of members of X with weight n. So for example, beta 1x is a single bracket here X, beta 2x is you take X and Y, X and put the bracket here, and this is a bracket arrangement, for example, an example of a bracket arrangement of weight 3. So we extend the operation star to an operation this. So what is the operation? So on beta x we have an operation star here, which is say b star x. You just enclose the bracket b. B is a bracket arrangement and c is a bracket arrangement. So this is another bracket arrangement of weight m plus n, where m is a bracket arrangement weight of m b and weight of c. So this is already an operation on beta x with respect to weight. It is already a monoid. It's not monoid. It's not a monoid. It's just a free what one calls the magma, free magma. So for example, so these are the things which you have here. So we extend these operations subject keeping in mind that we are looking at the multiplicative algebra. We have to have the identities which are satisfied by the multiplicative algebra. So first we define the the identity. We can obviously extend it by E is the empty word, as you know. So E star W is simply E. This is something, this has to be satisfied because E star the is always identity for every W. So derived from the usual identity. So observe that every element of f beta x has a unique representation as a reduced word in the latest beta x. You see, this is not fx, this is f beta x. It's a free group on the bracket arrangements beta x. So it's a large group. F beta x has a unique representation as reduced words in beta x. So we define u we extend this by induction on the length of u. The length of the reduced word, freely reduced word u, which is a member of beta x for u. So if length of u is 1, then u is b, and u is b inverse for b belonging to this. I'm sorry, this battery is running Okay, yeah. So, yes. Yes. So, yes. Okay, so B is a B star. So if B is you again use the induction on the length of the word W. So it is double induction which is being used. So length of word is this, and then W is C. So again we use the induction on W. So the second, first we have used induction on U. Here and then the induction on W also. So if W is C, then V star is just already defined here, and if W is C inverse, then we use the identity fifth of the proposition which we have already derived, so that it becomes remains multiplicatively algebra. We extend the star to star cap tilde by putting this. So this is the forced definition. So this is the step here. Now this is something which I have given over here, explained over here, when U is B and U is B inverse. And again we using a similar kind of induction, which I am not going to tell you, which you can see perhaps here. We can extend this operation on beta x. So now this on f beta x we have introduced this is star operation, and let S be a subset of f beta x. Okay, so f is a subset of f beta x, and gamma s denotes the subgroup of this generated by. So anyway, we want to have the multiplicatively algebra, so group has to be side by side. So generated by this set where U belongs to S, and f beta x, and S was a subset of f beta x, and we have already defined this star tilde here. And so this is gamma S, and inductively we define gamma is as gamma 1 S to be gamma S, and then gamma is plus 1 S as gamma of gamma is as defined over here. In this case, so let us denote this this by S. Evidently, this is a normal subgroup of f beta x, and in particular, consider the subset this, which again comes from all those five equivalent five trivial relations on this. So look at this S. So in particular, consider the subset omega here at the place of S, and look at the subgroup generated by omega and call it L of Fx. And this is indeed the free Lie algebra on X. You can define the product here and the star over here as this, and this is a free Lie algebra. Indeed, we were forced to define the way we defined was indeed forced definition to make this a multiplicative Lie algebra, and it satisfies the universal property. Observe that any the map I from X to L of X given by Ix is equal to this is an injective map. It follows easily. Evidently, LF defines a functor from the category of sets to the category of multiplicative category of ML of multiplicative Lie algebra, which is left adjoint to the forgetful functor from ML to set. So if you forget the multiplicative Lie algebra structure on a multiplicative Lie algebra, so you get a functor from ML to set, and this is adjoint to that. So if you take a group G, so similar construction holds for G. So G, so far the set X had nothing to do with the group structure. Now here G is a group with the binary operation dot. Consider LFG treating G as a set, and let S be the set, the subset of this beta G, which indeed was the multiplicative defining relations for G. So look at this S and S union omega, and look at the earlier defined S union omega gamma S here to define the multiplicative Lie algebra here. So therefore, this LFG is again a free multiplicative Lie algebra on G. So free Lie multiplicative Lie algebra is subject to the condition that G is a group. So in other words, if you take the multiplicative category of multiplicative Lie algebra and look at the forgetful functor, which takes the multiplicative Lie algebra to the corresponding mother structure group, then this is the adjoint to that. So this is the Lie algebra, this is a functor from this to this, and you get this So this is multiplicative Lie algebra. Now next we consider the concept of presentation of a multiplicative Lie algebra. So let K be a multiplicative Lie algebra and X be a subset and R be a subset of F beta X. Then XR together with a map F from X to K is a multiplicative Lie algebra, is called a presentation of the Lie algebra K, multiplicative Lie algebra K, if the induced map L F cap from L F X. So to K is a surjective homomorphism of the Lie algebras whose kernel is precisely the R union omega, the earlier trivial kind of relations, which were derived from the definition of the multiplicative Lie algebra, modulo this. So we get a surjective homomorphism this right with the kernel with kernel as this. More explicitly, we have a short exact sequence which is described over here in this equation. So R is called the, as usual in case of groups, R is called a set of relators, and you see a set of relators has to be added with the trivial relators defining multiplicative Lie algebras omega, so to say, to make it in the multiplicative, the ideal generated by LFX. So this is this. In particular, we have a canonical standard multiplicative presentation of this Lie algebra R and here. For convenience, this also will denote by this. This will all denote simply by R. Thus, for example, if a star is trivial, then the above presentation is the same as that for group. So, if you take a star to be trivial, then it comes out to be group, the usual group, the presentation for a group, the multiplication presentation for the group. Recall that a presentation for a group is the trivial as described. So, given a set X, leading presentation can be defined as usual. So now, as you know, so now I'm coming to the crucial point, the Lie exterior square. The Lie exterior square, which is a crucial object in our considerations. So recall that the Schur multiplier of G, when of course Schur multiplier RHG can also be viewed as the group of commutator relations modulo the universal commutator relations on G. Only three relations, you remember, only three relations. Those two relations which were also universal commutator relations were the problem for all the discussions. So on the same lines, we introduce and describe the Schur multiplier, or H, the analog of that HG, which we may call to be H cap or ML of G, of a multiplicative Lie algebra as multiplicative Lie algebra for relations on the among the commutators, Lie products and commutators in K, modulo the universal relations among the Lie products and commutators as described in the proposition 2.2. So 2.2, 2.2, there were certain commutator identities which I am looking. So now remember, for a multiplicative Lie algebra, okay, you had two operations. The product is there, and then the star is there. So with the product, if you take the commutator, it is the usual the improper multiplicative Lie algebra, and the star was the real thing which defined the multiplicative Lie algebra. So we have two things, the A cap B corresponding to this dot. If you look into the exterior square kind of thing here, for dot we have A cap B, and for this star for A cap the commutator we put that notation this, and for star we take this notation of universal symbols. This is here we are just trying to mod out the difficulties in having the obstruction as defined by three operations while defining G cap G, the exterior square. So this is something which is important here. So K cap L cap, now here is the multiplicative Lie algebra square which we are defining of formal symbols A cap B, A B belonging to K, and A B star I mean, this is for multiple. And then look at these relations. So these relations are the usual relations which were defining relations for the multiplicative Lie algebra. In other words, we are having two multiplicative Lie algebras on G with the help of A cap G and A B cap. All these relations are satisfied, except a few of these are the compatibility conditions mostly. So as you see, that the relations A cap G are same as those defined for by the symbol this, except the compatibility relations, this fifth and eighth and ninth, fifth, eighth and ninth. So this and this eighth and ninth here. So these are the relations which are compatibility relations between these two. And look at the amalgamated kind of free product of the multiplicative Lie algebras here. So this is what is K. So K cap may be viewed as a quotient of free multiplicative product of non-abelian exterior square of the multiplicative Lie algebras with non-abelian exterior square this of improper multiplicative Lie algebra with the multiplicative Lie algebra K cap modulo the ideal generated by those relations. And note that this is the non-abelian exterior square of K. This one is the non-abelian exterior square of K, and this, if you go for this, is the usual Schur multiplier for K. So we are looking at this. So this is the free product. So we can talk of the concept of the free product as we have already defined the concept of introduced the notion of presentation of the multiplicative Lie algebra. So that can be introduced. So the proposition 4.2 proposition earlier as described describing the identity is a unique homomorphism chi as usual for in case of the exterior square, the usual exterior square. We have a homomorphism K cap K to K. This is a multiplicative Lie algebra homomorphism, and we have a short exact sequence this of multiplicative Lie algebras as there also we had. Now there it was K star K was absent over there, and this kernel chi kernel eta there was HK, and so this can be called to be HML K here. So this is the functor HML which is introduced over here. So that is so I have I think I have 15 minutes yet. Is it? Hello? 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 Are you able to listen to me?
Yes, sir. Sir, continue.
Yes, sir.
15 minutes. Am I right? At least. Hello? Hello, Shubha?
Continue, sir. Continue.
Okay, thank you so much. So we denote this. Now I'll quickly describe the homology theory of multiplicative Lie algebra, which is indeed imitation, more or less imitation of the corresponding homology theory for groups, provided we have those. So we are interested in the central extensions, mostly the central extension. One can talk of the general extension and general homology theory also. Of course, the higher homology theory is not admissible over here, as we don't have the concept of the corresponding KZ module and so on. So that is that is something which is existing and not so clear. So anyway, so this is the central extension of H. Yeah. So evidently H is an abelian group here. So this H is contained in this. So as it follows that H is an abelian group with trivial D product. Although H is abelian, we shall use the multiplicative notation for that. We are not comfortable with the additive notation here in this discussion. So as usual, this is also an extension of group, the central extension of a group. So therefore, we have a two cocycle of K with coefficient in the trivial trivial K module H. So we have Ft for every section T. If you take a section T here, a map from K to G, such that T composed with beta is identity. So this FT introduces this. Every section induces a member of the 2 cocycle Z2QH as usual in case of groups. So I'm not going to so these are the identities which are obviously satisfied by those things. So it is the usual group homology thing. So every element in G is uniquely expressible as HTX. T is a section as a group consideration. So where H is in H and X is in H, the product dot and star is already given by this as usual. But now, so far the star, the things change. So far, further there is a HT, another map HT. So not only cocycle FT, we have another map which is apart from the cocycle HT from K cross H to this, which is given by the equation this. And this equation, this HT, looking at the different identities which are satisfied by the commutator, which are satisfied by the defining relations, defining conditions for the multiplicative Lie algebra. If we go into that and use this element suitably and do some computations, then we shall arrive at these identities which are satisfied by HT, the function HT. Thus, every central extension E of a multiplicative Lie algebra with a section T determines a multiplicative 2 cocycle FT HT of the multiplicative Lie algebra K with coefficient in the Abelian group these with a trivial Lie product in the sense of the following definition. So so all these F and G, so F and H, F is a 2 cocycle, F belongs to Z2KH, therefore H is a trivial K module, and H is so FH satisfies all these 12 to 16, 12 to 14 the conditions. 16, the conditions this. I'm sorry, this is 16, somewhere something is, no, 15 is here and 16 is here. So this is the conversely, if you are given such a 2 cocycles, then one can define the product structure. The product of the group has already been defined as usual, and this can be defined as usual. So now the multiplicative. Now, if we change the section, then the F and G are related by these identities. F, S, X, Y, the corresponding to 2 cocycle F, S, H, HS related with FT and HT with the help of these formulas. And FT and FS are also related as a 2 cocycles. So that means this is the co-boundary of a map G. Delta G, you remember, delta G, GY minus in additive notation usually it is written as delta G of XY is GY minus GXY plus GX. In multiplicative notation, if the group is non-commutative, in that case, this is the identity which is satisfied. So this is the trivial cocycle in case of group, as you know. Delta G, this is the co-boundary in the usual thing. And similarly here, HT has the co-boundary kind of thing here. HT and HS differ from the map. G satisfies the property that they differ by G X star GY inverse. So this prompts us to have the equivalence between the 2 co-cycles, multiplicative co-cycles of the multiplicative Lie algebra. And if you look into the set Z2KH of all multiplicative 2 co-cycles here, then it becomes an abelian group with respect to this product, which is as in case of usual. And HH dash also satisfies all those conditions, defining conditions can be easily observed. And the pair delta G G dash. So delta G is the usual co-boundary operator. Delta G of XY is dy by GXY inverse into GX. And G star, the condition which I already satisfied, is a map from K cross H to given by delta GXY is this, and G star XY satisfy the condition this. Can be easily seen to be a member of Z2K. This is also 2 cocycle, and this is what we call to be the co-boundary, 2 co-boundary. So so given any map from K to H which preserves identity, G has to preserve the identity also. So G map KH to the group identity preserving transformation. We have a map Chi from map KH, set of all maps from K to H, identity preserving map, not homomorphism. Map from K to H, identity preserving, to Z2K map, 2 cocycles by the Chi G is delta G, where delta G was defined here, and G star was defined as here, G star XY is GX by inverse. So the image of chi is the group of multiplicative two co-boundaries of K with coefficient in H, and it is denoted by B2 MLKH, and the quotient group, this is called the second cohomology group of K coefficient in H, and it's denoted by yes H is a multiplicative algebra. Yeah. So here already H is, this is an extension of H by K. So H is already multiplicative product, and H. So am I audible? Hello.
हाँ सर सुनाई दे रहा है।
वॉइस इज इकोइंग सम
इको आ रही कहीं से।
यस सर।
एक्चुअली क्या है कि मैं बहुत इलिटरेट हूँ इस सब चीजों में, मैं इसको बदल करके तो सामने आ भी नहीं पा रहा हूँ। So I'm sorry for the kind of thing. I'm orthodox kind of thing, and I prefer backboard and so on. And
so now it is okay. Now it is okay,
sir.
I'm sorry actually. So bear with me. I hope. Yeah. So is it okay?
Yes
sir. Okay, so this is H2ML and H2ML. So you have this. This is the second cohomology of multiplicatively algebra H2KH, where K is a multiplicatively algebra and H is an abelianly algebra, that way, which we described with the trivial Lie product. So this is, and then we get an exact sequence like this. So chi is a map from map KH to this. So chi of F takes delta F as defined here. Chi of G is delta G star. G is an identity preserving map, and chi is delta G star. So this is where U is the quotient map. So further, we have a natural projection map P from Z to KH. So you know Z2MLKH was the set of elements FH. So F was already a 2 co-cycle. So you have a mapping projection map from this to this, defined by PFH to this. Evidently, P of this, it can be easily seen that the boundary of this is contained in the usual co-boundary in case of groups. So thus P induces a homomorphism from the multiplicative algebra to the usual multiplicative, second cohomology group of K with trivial K module H, usual K module H. So multiplicative, the second cohomology of multiplicative algebra, considering multiplicative algebra, and here we are considering as a group only, not multiplicative algebra. Given by this, the homomorphism P bar need not be injective. And for example, here the trivial example has already been given. It turns out that it's not injective, and indeed it is not even surjective. It is not even surjective. More generally, we have the following proposition, which can be easily seen. If H and K are abelian groups with a trivial multiplicative algebra, even then you see that H2, the multiplicative the cohomology, is the second cohomology here, and the group of homomorphism from the exterior square of K to H. So that is usually, that is not difficult to observe. So this is so now suppose that this is a multiplicative algebra, and you have this concept, and here this proposition can also be easily established, which I use here. The kernel of the homomorphism P cap, which we have defined here from this, is isomorphic to, indeed it is isomorphic to the exterior square modulo J. And what was J? J was really the obstruction for those additional commutator identities too, where WK is the non-abelian exterior square, and J is the subgroup of K generated by this, coming from the Jacobi's identity. But you know here that here star at the place of star, cap cannot be placed. So cap cannot be placed, and that was the basic problem initially to introduce those things as for multiplicative things as usual. So this is the theorem. This is the proposition which is is here. So for example, if you take H here, so it's a multiplicative algebra here. Suppose H2KH H2 multiplication. You know, if K is a finite group, then you know the usual Schur multiplier, the exterior square, the usual Schur multiplier is a finite group. It's a fact that you already know, that we already know, that if K is a finite group, that is a Schur Hopf formula for the group that was proved by Schur, as you know, coming from that. So it is that the Schur multiplier, the exterior square is an extension of the Schur multiplier by K, as you see that if K is finite, the Schur multiplier is already finite, so this is also finite, and J as a normal sum, this is finite, so therefore this is also finite. H2 MLKH, this is a crucial fact which will be used, for the, so therefore this is also finite. So actually, as the important formula, the Schur Hopf formula for multiplicative algebra, as you see, is precisely the H2 MLK C star at the place of H. If you have any divisible kind of thing, or C star, then that is isomorphic to the usual those formula which are already stated in terms of the free presentation. In terms of the presentation, free presentation. So this is something which is important, that this is finite when K is finite. So that is the thing which follows from this. This is the formula, and if K is then this is this, you know, K is in these two. So that is also there. So and you know. That if G and A be multiplicatively algebra, as usual, you can talk of form GA with the set G of all Lie algebra homomorphisms from G. If A is an abelian group with a trivial Lie product, then this is also an abelian group, and you have so if this is a central extension of this, and suppose from H to A, any abelian group A here, you are given a homomorphism. From H to A, you have a homomorphism. Then any homomorphism here, and you take a member of H2KL, so that is given by FH. So any member of H2KL is given by the two cocycle FH, the class of two cocycle FH, and here is a homomorphism. If you compose with F, which is a homomorphism from K cross K to H, with that homomorphism from H to A here, then you get again a multiplicative 2 cocycle with coefficient in A, and it is an easy observation, as in case of groups are here as already given here, that is also preserved the co-boundary if it is right. So therefore you have this exact sequence. This is what is called the fundamental exact sequence usually. And if in addition we take A to be an abelian group, for example, if C star is there, the multiplicative group of complex numbers, then it is then image delta, the image of this is precisely GG. This is an important point in home G star G intersection H. A home GG. So this is something which is easy to observe. It's not very difficult, and more or less leaving at certain extra verifications. It is usual proof of in case of groups. So it's not very. So if this is a central extension with the, for example, C star, which is a divisible group, the corollary of that, this is a subgroup of that. So H2 is the character group of this home HK C star. So therefore, you see that H2 MLK star is the character HK C star of HK of the multiplicative Lie algebra, where HK was already described as a for a group. So, however, if K is finite multiplicative Lie algebra, then we shall see that again this is a finite group. This is an isomorphism, and as observed, the Schur, the crucial step of Schur, which perhaps I pointed out that the crucial step in proving the Schur Hopf formula was that if HH, if the central quotient of G is finite, then the commutator is also finite. That was the crucial step in proof of the Schur Hopf formula, and that is really the crucial thing for here also to be done, and that is what is the crucial thing which is done here. So I think I'll I'm running out of time, but anyway, so I'll take some more time to do that. So now, as you know, this was up to this the exact sequence. It was up to this it was already exact sequence, but if it is a free central extension, so the concept of free central extension is something which is here a central extension. This is as usual in case of groups. So this is a free central extension of multiplicatively algebra. So recall in case of groups, this is how you define free central extension for in case of groups. So this is a free central extension if given any morphism, any homomorphism, so multiplicatively algebra homomorphism from K to K dash. It can be, it can be the diagram. The diagram can be completed. I mean, you have a unique homomorphism from G to G dash and a unique homomorphism from H to H dash, such that this diagram is commutative. The diagram coming from E to E dash, we have a morphism of the short exact sequences. So that is the kind of thing which is here. So if then we say that it's a free multiplicative, it's a free central extension, and free central extension exists, and it is indeed this. If you take a free presentation of the group K, then this is a free central extension of the group this. Okay, I'm sorry, F has to be here. R star, RF, R star, F. So anyway, this is the free extension, because if you take RF will come here. So this is a central extension. RF, if you take the commutator over here, it comes out to be here. The commutator this. So this is a free central extension. So if you have a free central extension, then this exact sequence, which is exact sequence till this point, leaving one, is exact even if it is if we add one, provided this is a free central extension. So we had that free central extension, and we had that. So therefore, let this be a free. So therefore, it follows that H2 MLKC star is isomorphic to this, as this is exact sequence, as you see. So there, and H2 MLK star, and earlier we observed that the image of delta is what we have observed is this one, which we had observed. So this is H2 MLK C star is isomorphic to this. This. Okay. So now this is there. So so for finite group, indeed, this will be isomorphic to this as and you know, if K is a finite group, then H2 MLKC star is a finite group of order, such that the order of each element divides the order of this. Recall this formula as we have as we described from H2 KL to H2 MLKC star. We had that P bar map whose kernel is this K. This star. If we use this, and we use the already proved fact that the Schur multiplier H2KC star, all elements of this divide the order of the group K, and K to K, if you use this property, then you can easily see that the elements of this divide this. Now here comes the crucial fact that if G is a multiplicatively algebra and such that this is finite, then this is also finite. Recall here, remember here that if LG is trivial, LG is contains ZG, LG contains ZG, the usual group central extension here, then G by ZG is finite, implies that GG is finite, because G star G will become trivial in that case. So the usual Schur Hopf formula follows from here. The result of Schur, the crucial step including the Schur Hopf formula, that follows from here. So this is the star. This is finite, and this is a fact which is more or less follows from the fact that C star is a divisible group, and applying suitably the second isomorphism theorem, which I'm running out of time, so I should have done on this, you know, on this pad, but the pad I have, but I'm not, you know. I'm quite illiterate, as I have pointed out. So it's isomorphic to the subgroup of this, as you see. And if you use that fact that this is finite and use it for the free central extension, then the free central extension, then you see here that this fact, the commutator of this, the central, this by the center is finite, that comes from the earlier consideration, and therefore this is finite. Once this is finite, you see, if this is finite, the home of this is finite, so therefore this is isomorphic to this, and that gives the Schur Hopf formula that H2 MLK star is isomorphic, C star is isomorphic to this, inside this. So that is the Schur Hopf formula, which follows here the Schur Hopf formula. You see that the commutator, this is really contained in the center of this as here, and use that fact. So therefore this is so therefore this is the but apart from this, so this is the Schur Hopf formula, which is a crucial fact. And you know, the concept of presentation of multiplicatively algebra. So I just wish to make it yes. So am I share? Okay. So now, am I visible now? Am I visible
Yes,
now?
No, sir.
Yes.
Yes,
Am I visible now?
Yes, sir.
हाँ sir, yes sir.
So then, see, if you the usual K theory business is also incorporated over here. So I'm unable to write it anywhere what to do. Whiteboard is not here. So anyway, so okay. So usual K theory thing. If you look into the Steinberg groups, so Steinberg groups, there are three Steinberg relations which are satisfied by the elementary matrices. Eij lambda, if you remember, Eij lambda into Eij lambda, Eij mu is equal to Eij lambda plus mu, and so on. And similar relations about small Eij. Small Eij is lambda is the matrix. All of whose entries are 0 except the Ij entry, which is your lambda. So if we use the different Steinberg identities for additive and for the multiplicative thing, and use the Steinberg multiplicative Lie algebra and look at the Schur multiplier, multiplicative Schur multiplier of that is really the product of the usual multiplicative Schur multiplier of the group with the additive Schur multiplier of the additive K theory. So that's the relation. So I'm sorry, actually, I made a little mess of it. So that is there. So, thank you. Thank you. So now I have to come to, yes.
Yes, thank you so much, sir.
So if you wish to ask, unfortunately, I have the better thing would have been that I would have on the slide I would have done something that I couldn't do. Of course, somebody has given my daughter has given it to me, but still I'm not competent enough to do that. So I really apologize for that. So that is why I had to do a little bit of work also to be safe and so on.
Thank you so much, sir, for sharing your knowledge with us. We are privileged to have your live lecture, and this lecture will be definitely very grateful for.
And the other is the commutator multiplicative algebra structure. None of them are free. Of course, as Magnus says, that it will never come out to be free. So because the defining operations are, you have relations given by the group G. For example, you take V4. For example, you take any multiplicatively ring. So, for example, so Lie ring you will take. So that is not a free Lie algebra. Is a universal object, which is just a construction on a set X. So, and you remember, given a group G, we defined some kind of free object on group G, taking G as a set, and then modulo taking the quotient modulo the relations which are satisfied by G. So that is what that. Just as here in case of that Lie exterior square is not going to be GG, the usual the commutative subgroup. because the commutative subgroup. You see, one of the problems maybe is that given a group G, how many multiplicative algebra structure can be defined on G? What are the multiplicative? So initially, I motivated the concept of multiplicative algebra with that it amounts to have a homomorphism from the homomorphism from it amounts to have a homomorphism from earlier we defined it amounts to have multiplicative. Okay, yeah. So it amounts to have a homomorphism. Homomorphism. Right. Yeah, here you see that it amounts to have a homomorphism from G cap G to H cap G to G. So given any G equivalent homomorphism, you will get a multiplicative algebra structure. So given a group G, to just for example, in case of finite groups, Sumit has tried to do something for finite groups, some cases. Anyway, so this is a multiplicative algebra. It may be helpful for him also. So homomorphism, G equivalent homomorphism from this to this. So there are groups which are least simple groups in the sense that you cannot have any other multiplicative algebra structure on that group except the usual one, the improper one, the commutator one, and the trivial one. For example, free group. For example, the simple group. And for example, there are other groups also with the trivial Schur multiplier. Trivial Schur multiplier has to be there. So that is there. So this is so you have plenty of examples of such groups. So. Right.
Thank you, sir. Thank you so much.
Yeah, any other questions?
Yeah, please ask if you have anything. So the way I motivated the multiplicative, actually I don't know whether probably the ILS had the idea to how to describe the set of all commutator identities of a group. So can we have some kind of free things which covers all the universal commutator identities, just as in case of those which are described by those three identities. So that was perhaps the problem, which obviously 5 identities are not sufficient. All those Philip Hall identities and those 3 identities for groups that are plenty of identities are here. So that is here. Yes.
Okay, I guess there is no other question. Thank you so much, sir, for your time and words. Your presence and wise words helped magnify our cause in the best possible way. We are very grateful for the time and effort you took to share your thoughts and experiences with us. Once again, thank you so much, sir.
I couldn't get the whiteboard, otherwise I would have preferred to write the truth.
But still, it was very nice, sir. Thank you, sir.
Thank you all for your kind and patient hearing the lecture. Maybe it might have been,
yeah. Now, since we are running a little out of time, so without any delay, we will start our